So let's do an example. Let's revisit this example where we throw a dart that lands uniformly inside a circle of radius r. So, this is r comma 0. This is negative r comma 0. This is this point over here is 0 comma negative r, and this point here is the coordinates of this point is 0 r. Okay, this is our x-axis. This is our y-axis, and maybe I want to know something about the distribution of the y-coordinate given x. Okay, if I know that x falls here, then you know what is the y-coordinate? How does that tend to behave? So to answer that, maybe I can to shed light on that. Maybe I can want to calculate the conditional density of y given x. Okay, find this function. First of all, I'm going to conjecture. I'm going to guess at it. This is a good exercise to do whenever you try to tackle a probability function, probability type problem. Can you intuit the answer at all, or can you see a quick way to do it? Gosh, what should it look like? I know what the marginal density function for x is, and the marginal density function for y, they are not uniform. But if I'm given x, if I'm given that this is x, then where do you think the y coordinate is? I think it actually is uniform. I think this is uniform in this region. Maybe you should think about that. I'm going to conjecture that this is some constant. For fixed x, and then of course times the indicator function. I guess that absolute value of y is less than or equal to r squared minus x squared. This indicator function just says that this conditional density function needs to be 0 whenever you step outside the circle, right? If I fix, in fact, and I need to also stipulate that x needs to be between negative r and r, I think. Yeah, in fact, so maybe I should say undefined if x is not in the closed interval negative r to r, right? All right, so let's hammer this out. Conditional density function for y given x, by definition. This is by definition. If we define this to be the joint density function of x and y, well, y and x, same thing actually, because it's there we go. X and y, I guess, but there we go. Over the marginal of x, there we go. Now, if you remember, or even if you don't, the top part here, we found that to be 1 over pi r squared, right? And then times the indicator function that x and y, that are random points there, x and y, are indeed inside the circle. Can I just write it like that? Inside the circle, like that. And then divided by, remember we got the marginal the marginal PDF for x to be 2 times root r squared minus x squared all over pi r squared. And then this will be times the indicator function that x is between negative r and r in that closed interval there. Okay. Now you can probably see that these guys are going to cancel, and you're going to be left with the indicator function of x. Another way to say this, that x and y are in the circle there, is that x falls between negative r and r, and big fat and y falls between let's see, negative root r squared minus x squared and positive root r squared minus x squared. Okay. All of that over 2 root r squared minus x squared times the indicator function that x takes on a value between negative r and r. Okay. Now, here's a trick that's really useful. I don't think we've seen this before, but one great thing about indicator functions, here's a fun fact for you, and it really is fun, and it's also really a fact. The indicator function of this statement called A and B is the indicator of A times the indicator of B. Okay, that is, both A and B are true if and only if A is true and B is true, right? So if both A and B are true, this evaluates to 1. If A is true, then this is 1. If B is true, then this is 1. You get 1 times 1 is 1, and they're equivalent. If either A or B is not true, then this will be 0, and this right-hand side will also be 0. So this implies that my conditional density function of y given x can be written as the product of a couple indicator functions at the top there, right? That x is between negative r and r, and the indicator function that y is between negative root r squared minus x squared and positive root r squared minus x squared. Okay, all over 2 root r squared minus x squared times the indicator that x is between negative r and r. Okay. Now, I think you can see that I was right. That for fixed x, this guy is in fact it's a constant. Okay, it's a constant. If I fix x, then this conditional density function is in fact it's just 1 over 2 root r squared minus x squared for x maybe this is a clearer way to write it for x in negative r to r. This is just 1 over 2 root r squared minus x squared. Okay, times the indicator that y is where it's supposed to be. Y is between shoot. Let me rewrite this. It's 1 over 2 root r squared minus x squared times the indicator that y is between negative r squared minus x squared and positive r squared minus x squared. This is for x between negative r and r. What if x is not between negative r and r? That is, if x falls outside the circle, what is the density function for y? It's really not defined. Okay, it doesn't make sense to talk about it. Technically, density functions have to satisfy certain axioms, right? Like they need to be strictly non-negative, but they have to integrate to 1, right? So if I have an x value that's out here, and that occurs with probability 0, then what does the density function look like? Well, I don't know. Maybe it looks like, I don't know. There's no way to tell. There's no way to tell, and it doesn't really make sense to talk about it. So we just won't define it. It's undefined for x outside that interval. Okay.